i samband med det.
What we can do about it as individuals and jointly in our societies. We do this in the spirit of Alfred Nobel, to the greatest benefit of humankind. Dialogue is a key word in this context. We want all of you who are here, but also all of you who follow us digitally, to participate in our conversation. Water matters is the heading of today's conference. It is truth. Water is life's matter and matrix, mother and medium. There is no life without water, said a former Nobel laureate. As for myself, after last summer draft here in Sweden, and not least in the archipelago where I spent my time, Benjamin Franklin's clear aphorism, when the well is dry, we know the worth of water goes a very long way. Indeed, a great sense of urgency should characterize the meeting on climate change that is going on in Poland right now. Today we will examine water from many perspectives. We will look at the importance to the human body, but also to our ability to live and to survive. And we will explore the role of the sea, not least for climate change. And we will also travel to the bottom of the sea. And we will not be content with our own planet. We will in fact travel to Mars. Water also awakens feelings. In a drop of water are found all the secrets of all the oceans, said a Lebanese poet. We will today encounter the role of water in a performance lecture. And finally, we will discuss solutions. In the end, this is about politics, serious politics. Today, as we cover a wide range of topics, from science to politics to art, we are acting entirely in the spirit of Alfred Nobel. He was very much a Renaissance person. He believed in the value of facts and knowledge, and he wanted to work for peace. In times like this, it is more important than ever to highlight what the Nobel Prize stands for. And it is in this spirit that we organize exhibitions and discussions, produce digital material and organize conferences like this. We've done this more and more in recent years. And next year we will be in Santiago in January, and we will be in Japan in March, in Madrid in May, and in Berlin in the fall, and we might also go to India. There is a huge and gratifying interest for what we are doing, especially among young people. It's also in this spirit that we will try to create a Nobel Center in Stockholm, despite the reversals of last year. A place where knowledge will encounter culture and politics just like today, but all the year round. This idea is simply too good to give up. Let me once again thank you all for coming here to this day about water, featuring discussions and dialogue. Our special thanks to Carl-Bennet AB, the City of Gothenburg, the Västra Götaland region, and Ericsson, who have helped us with Nobel Week dialogue over all these years. A frog does not drink up the pond in which it lives, they say. Will man live up to that? Let me finish with that hope. Thank you.
Well, hello. It's a very great pleasure to be back here as your guide to today's meeting once again, and it's an enormous pleasure to see this wonderful full house. Having got you all in here, the first thing I need to do is to tell you how to get out again, just in case something happens. So if you could all just please take a note of each, off into space, back into our bodies, and down towards a molecular level. And I think it's true to say that at the end of this day, all of us are going to look at this in a slightly different way. Now, to get us started, I'm delighted to welcome Johan Rockström to give us an introductory talk on the future of humanity on Earth. Thank you.
Your Royal Highness, dear colleagues, friends, we all share the nervousness of living in a turbulent time. Everything from what will certainly be remembered as a year when the Earth system for the first time sends invoices back across the whole planet, starting with the deaths in Japan with heat waves and flood, over 200 deaths, all the way to the unprecedented forest fires in California, the floods in Kerala, the heat waves in Europe, something that occurs at 1 degree Celsius warming. Connect that with the geopolitical turbulence of the uprisings in France, Brexit, Bolsonaro, the uncertainty in Australia. We live certainly in a world where we're not really yet at a point where we're truly seeing a transformation towards a prosperous, socially inclusive pathway for humanity on Earth. It's therefore at a Nobel Week, when positioning water as the bloodstream in the biosphere, as the core of the future for humanity, it's important for me to start by sharing what I would argue are the three most important scientific messages from science to humanity over the last 10 years. Number one, we've entered a new geological epoch. We're in the Anthropocene, anthros for humans. We're now the largest driver of change at the planetary scale. We're hitting the ceiling of biophysical hardwired processes that regulates the state of the planet. Second, we know with very high degree of certainty that the Holocene, the interglacial phase we've been in since the last ice age that we left 12,000 years ago, is such a remarkably stable state of the planet. It's an equilibrium within which we have been able to thrive and develop modern civilizations as we know it. It's our Garden of Eden that has stayed within plus minus 1 degree Celsius. The third insight is that we built up our societies believing that things change incrementally, linearly, and thereby predictably. But the reality is completely reversed. Resilience means that systems from rainforests to wetlands to financial systems can cope with disturbance during a long, long period of time until they break, cross tipping points, and can abruptly shift and no longer support humanity. Put these three insights together and it leads to the insight that we need planetary boundaries. We need scientific targets that gives us in green a safe operating space within which we can have prosperity, social inclusion within a stable Earth system. This, dear friends and colleagues, is what I would argue is the new definition of sustainable development in the Anthropocene. That we now need to become planetary stewards of the whole system where water fundamentally is part of the core. Now, the reason for nervousness when we meet in Stockholm these days is because what's happened just in the past few weeks. The World Energy Outlook showed us with some shocking information that global emissions are on the rise with 1.7% in 2017. We're back on unfortunate rise of increase. Yesterday, you had the brutal news published in The Guardian where the Global Carbon Project showed that 2018 is actually projected to be a 2.7% rise in emissions, even faster than over the past 15 years. This is occurring at a situation where we just, when we met in Paris, actually had some good news. We were starting to bend the curve of emissions. 2014, 2015, 2016, we're leveling off because we saw that now we seem to be reacting and acting on climate change. But unfortunately, we're back on this high level of emissions. Now the drama, which has water as its core, is the following. During these years when we leveled off, the World Meteorological Organization just a few days back, released a report on concentration of greenhouse gases, showing, as you see here, that the concentration of greenhouse gases is continuing to rise. But not only that, look at the numbers. 2015, when we met in Paris, we bumped through the 400 ppm mark, a place we haven't been for the past millions of years. Then it jumps up with 3 ppm in 2016, and another 2.2 ppm 2017. This is faster than even when we were increasing our emissions. And this occurs during years when we did not, as humans, contribute to rise in emissions. What is happening? Why is global warming intensifying even more, despite the fact that we seem to be increasingly doing the right thing? Well, we have the answer. And the answer is the biosphere. The answer is the hydrological cycle, the land system, biodiversity is no longer keeping its resilience intact in the way that we have seen it done before. What you see here is emissions to the left for fossil fuel burning, and the columns that go negative is the carbon sinks of carbon taken up in natural ecosystems on land and in oceans. 25% in oceans and 25% on land. Half of our emission of greenhouse gases are taken up by natural ecosystems, providing this world's largest subsidy to the world economy through its resilience. Now, 2015, 2016, we start to see the cracks in this system for the first time. Now, we do not know exactly why. It may be very much connected to the fact that these were El Niño years, where we have droughts and forest fires, which means that biomass grows more slowly. But we cannot exclude, or I would even argue it's very likely, that it's also connected to the fact that we are deforesting, degrading land, ruining ecosystems in a too fast pace where ecosystems have difficulty in keeping pace with our pressures. That is why water is so important. Temperatures continue rising. We just learned that 2018 will be the 4th warmest year on record. The 3 other ones is 17, 16, 15. So this is a bad trend. We also have research coming out. This research on the slide is not even published yet, showing that water and land are fundamental to the future to reach the Sustainable Development Goals. Here you see the most recent analysis showing that if we continue as we do today, and if we would really try to stay within the planetary boundaries, we would have to reduce food production with 50% on Earth to come back into the safe operating space on water, land, biodiversity and nutrients. But the same analysis showed that we have potential through the technologies we have today to increase food production with 100% through sustainable intensification, which means that we actually can achieve the Sustainable Development Goals through a transformation of the global food system, moving away from unsustainable plow-based systems and intensive mechanized agriculture to more crop rotations, more biodiversity-based ecosystem approaches that works more closely with nature through, for example, conservation tillage and water harvesting systems. It is possible. This study was just published by Marcus Brinkman and colleagues for the first time, checking what will it take for us to stay within planetary boundaries in the food system. On the y-axis here you have the different boundaries from greenhouse gases to blue water is the middle one, which is mostly green, nitrogen, phosphorus. And what we're looking for is to be in the green space, meaning where the food system actually operates within the safe operating space of planetary boundaries. Don't go through all the details in this slide, it's just the key message is that the only food system that takes us to a safe space on Earth is if we transition into water-efficient, really sustainably intensified, flexitarian diets where we reduce food waste with a factor 4. This is truly not only a food system revolution, it's a behavioral change revolution for us in terms of changing diets. 4 billion people on Earth live under conditions of water scarcity, over half of the world population today. We know scientifically today also that geopolitically water is really sensitive. What you see on this map is science indicating in red the regions that depend to 80% or more for their rainfall on upwind evaporation. What this means is the following. Look at China here, which is in red. they depend to more than 80% of the rainfall evaporating from the forests in Russia and eastern parts of Europe, meaning that the way the countries upwind manage their ecosystems depend on the downwind availability of fresh water and therefore stability in societies. We have recently shown that this has even larger implications through the hothouse Earth analysis, indicating that if we push global warming too far, if we erode the biosphere too far, we risk crossing tipping points that can lead to domino effects where even 2 degrees Celsius warming could bump us up to another 1/2 degree to 2.5 degrees if we cross tipping points that can start processes of tipping according to the hothouse Earth analysis, showing that 2 degrees Celsius warming is not only about minimizing the impacts of adaptation, but it's also a question of avoiding crossing tipping points. And let me just share with you 2 of these risks of tipping elements here, the jet stream and the thermohaline circulation. Now the Gulf Stream, which is part of the ocean circulation of heat, is slowing down. This is a nervousness from science, not indicating yet that we're at a tipping point, but it's recent findings showing that the big conveyor belt of heat that is flowing up warm water from the equator and releasing back cold deeper water back to the equator, is slowing down. That can affect the living opportunities in this part of the world here in the Nordics. Now, the second one is the jet stream, which we're starting to see indications that it's behaving so weird because this high wind system in the upper atmosphere that depends on the gradient between a cold Arctic and a warm equator, when the Arctic is warming so fast, twice as fast as the rest of the planet, that gradient is weakened. The jet stream becomes weirder and locks in high and low pressure systems that could explain the heat wave we saw in Europe this year. So you see sudden, surprising, amplifying effects at 1 degree Celsius warming related to tipping points in the Earth system. So it's not surprising when the IPCC released the 1.5 degrees Celsius report. For the first time, science is very clear saying that actually 1.5 degrees Celsius is not only about impacts that can hit social, economically today, it has a very strong scientific support in terms of being able to stay within a safe operating space. The pathway for the 1.5 degrees Celsius is shown here in green, which means bending the global curve of emissions no later than 2020, and actually reducing the emissions at a pace that means cutting emissions by half by 2030, cutting by half in 12 years, and reaching a world fossil fuel-free economy by 2050. That is the scientific knowledge today, and it requires what? Well, it requires that we actually do the same for nitrous oxide, methane, and keep all the natural ecosystems intact. So let me just close with some hints that it's actually possible to succeed. Together with Christiana Figueres, I presented this following exponential carbon action plan at the Global Climate Action Summit in San Francisco a few months back, showing that there's evidence that we actually can cut emissions by half by 2030 by integrating systems with land, water, biodiversity, and climate. Now what you see here to the left is the indication that carbon is increasingly being decoupled from economic growth, which is so positive. Over 40 countries have decoupled economic growth from greenhouse gas emissions, Sweden being one of them. To the right, you see the countries that have actually adopted a price on carbon, now being up to 50 countries. We see an exponential rise of action towards sustainability. But the most interesting is this. Together with Project Drawdown and Paul Hawken and team, we tried to really do wedge analysis of existing technologies to see sector by sector, can we cut emissions by half by 2030? And we indicate that yes, it is possible, from energy supply to industry, buildings, but as you see here, also in food consumption and agriculture, which is all about sustainable management of land and water. So this takes me as a closing kind of summing up to the Sustainable Development Goals. This major accomplishment of the world community of adopting an aspirational universal plan for humanity in these 17 goals. Science shows that we're not allowed to do what we tend to do today, which is essentially to operate them as a Swedish smorgasbord. We kind of pick our goodies and walk with one goal at a time. Science shows we need to operate these as a wedding cake. There are 4 non-negotiable Sustainable Development Goals which form the basis for a stable planet. It's water, it's climate, it's biodiversity, it's oceans. And beyond these, we can have aspirational social and economic goals that can be successful within these. We have science gathering to look at these transformation pathways to reach the Sustainable Development Goals in 2030 within planetary boundaries by 2050. It's a transformational journey of a new restructuring of the economy, of technologies, of equity. In January, we'll see the Eat Lancet Commission for the first time define scientific targets for healthy diets from sustainable food systems, providing science-based targets for society. We see increasingly science-based targets being brought forward to business as well. We mean business, the World Business Council, working very hard to get science-based targets for the Earth system, the 2 degrees Celsius equivalent for water, for land, for biodiversity, to be able to really transform in this direction. So my message at a meeting where water matters is, let's take a systems perspective. Let's take the whole Earth as our challenge today and say that yes, we can now transform and meet the Sustainable Development Goals within a safe operating space of a stable and resilient planet. And water matters more than anything on that journey. Thank you very much.
Reflects my mental temperament of being totally bistable. But anyway, I hope you are willing to eat a fast lunch.
Thank you both very much.
Thank you.
So, I was very taken by Maud Barlow's mention of the idea of a quiet mind. And on such a busy morning, it's quite good to take just a few minutes to settle down a little. So now we're going to have a musical interlude. Now I have to say, this actually looks a bit like my evenings at home, because my son is a cellist, and so he's to get him to do practice, I have to put his chair out for him and say, come on, there it is, just sit there. So there's the chair, and all we need now is the cellist. So I would please like to welcome on stage Linnea Olsen, and to accompany her, Maria Holmström. Please.
Mm-hmm. So now, nothing will disturb this weekend, my beauty. Now we're spellbound, everyone will spellbound. They're gonna carry me in King's Chair. They're gonna sing my name in big letters. Lead me out. Lead me out. Lead me
Dive into the deep ocean, and to take us there, I'm very pleased to welcome Diva Amon.
Okay, so good morning. My name is Diva Amon, and I'm a deep sea biologist. I'm from Trinidad and Tobago in the Caribbean, but I'm currently a research fellow at the Natural History Museum in London. So today I've been tasked with trying to ease us from freshwater into that of the oceans. And so to do that, we're going to go on a really quick journey. So the oceans are really the epitome of out of sight, out of mind. We're unable to see most of them, and for most of us, they don't appear to form part of our everyday lives. But now, more than ever, we're exploring, and we're seeing our oceans in a three-dimensional way, and we're finding that there is actually much more than meets the eye. Our oceans are the largest ecosystem on the planet. They give us 98% of all habitable space on Earth. And our deep sea provides us with ecosystem services that keep our planet healthy and keep us alive. It sequesters carbon, it regulates our climate, it detoxifies some of our oceans, and it also cycles nutrients. And it is increasingly being viewed as a source of crucial resources, things like minerals, medicine, food, and oil and gas. But the great size of this ecosystem comes with great responsibility. And yet, most of our deep sea is largely unexplored. We've actually seen less than 2% of our own deep ocean floor. However, the little that we have explored has shown us that the deep sea is not one big, dark, cold, homogeneous environment. Just like in shallow waters and on land, there are a variety of habitats. The most common of these are sedimented abyssal plains, some of which are turning out to be amongst the most biodiverse places on the planet in the top left. There are hydrothermal vents that gush superheated, mineral-rich black fluid and are swarming with endemic and uniquely adapted species in the top right. And there are seamounts, over 30,000 in fact, that have lush coral and sponge gardens, some of which may be thousands of years old, in the bottom left. And there are even lakes made of brine, 3 to 8 times saltier than that of the surrounding water down on the deep sea floor. And there are canyons, there are trenches, even the skeletons of whales form their own ecosystems, and the list goes on in the deep ocean. And it is because of that great variety of habitats that there is an incredible biodiversity of life. Life in the deep ocean pushes our boundaries It breaks paradigms of life, and perhaps it can provide solutions to some of the greatest challenges facing this planet in the future. But we're also learning that life in the deep ocean is very difficult. Animals grow and reproduce very slowly, making them incredibly vulnerable to change. And the deep sea is already under pressure. We see our litter, our chemical pollution, and even the effects of climate change on nearly every expedition we go on. Who knows what else is out there waiting to be discovered? New species of sharks, crinoids, corals, the oldest species on the planet perhaps, maybe new antibiotics, hermit crabs with anemones on their butts. But we can say for certain that if we keep looking, whatever we come across will not only surprise us, but it will be weird and wonderful in completely equal measures. So some food for thought as we look forward to this panel on the oceans. Pliny the Elder was a Roman naturalist, philosopher, and author, and nearly 2,000 years ago he said, "By Hercules, in the sea and in the ocean, vast as it is, there exists nothing that is unknown to us." And that was nearly 2,000 years ago. And of course, at that point, deep sea exploration had not even begun. And so that kind of mindset is exactly what we need to not have, because there is still so much to discover in our oceans. Moving forward, we need to keep working together so that we can better understand, better value, and better manage our oceans, not just for us now, but for generations to come. Thank you.
Thank you so much, Dean. Now, if you please take a seat.
Anyway.
Yes, go at the end there, that's fine. I would like to welcome some fellow panelists to help you explore the oceans. And that is Lisa Amelia Svensson, Julian Dowdeswell, and your moderator, Lisa Schultz. Thank you.
Thank you, Adam, and thank you, Diva, for your beautiful presentation that really took us from freshwater to the oceans. With me I have Lisa Amelia and Julian as well. It's great to have you all here. I'd like to start with bringing in the audience a bit, actually, because I think we all do have a relationship to the oceans. So how many in this room ate something from the ocean in the last week? Yeah, quite a lot of people. And how many feel that they have a personal relationship to the ocean, like you like to go and see the ocean for recreation? Yes, we love the oceans. And then actually one more thing, we just take one big deep breath together. And now we brought the oceans into the room, because every second breath we take is actually from the oceans. So, and I would like to begin in this panel with talking about the excitement of these regions, because Diva, you're in the deep sea, that's really a frontier of human exploration, and Julian, you've visited both Antarctica and the Arctic, these very remote regions. So what excites you about these places?
I think I'm fairly lucky in that, as a deep sea biologist, there are very few careers on the planet that allow you to be amongst the first people to see something that before that moment we had no idea existed. And so that is just the most incredibly exciting and incredibly humbling experience, I think. But not just do we get to see new animals, new habitats, new communities, but they're incredibly breathtaking. We once thought that the deep ocean was this sort of place devoid of life, but we're now finding that biodiversity there is unreal and just fascinating.
Julian?
I've always loved mountains, and I've always loved maps, even as a child. I was really lucky at school to be encouraged by my teachers, and I think that having good teachers is fundamental to one's future. At university I was exposed to the same sort of thing, and I led an expedition to the Arctic. I've been really lucky to have a career in science spanning several decades since then, and like Diva, I've been to some of the wildest places in the world. I've had the feeling, as a scientist, not an explorer, of going to some places that probably nobody's ever been to before. And also, the great thing about science is the more you find out, the more there is to find out.
And it takes an adventurous mind, doesn't it, to go to Antarctica and the Arctic?
Well, yes, and I think a flexible mind as well, because the polar regions, like the oceans, don't always let you do what you plan to do. And so we've always got a plan B, and even occasionally a plan C when the ice doesn't let us go to the first place. And sometimes we've had to completely rewrite the science on the hoof. But there is so many questions that you can ask that is always possible.
I visited Antarctica and I was struck by that you see the polar region, the ice is so dead, but then you see all that life underneath the water. So you see the waves and this, it's just so rich with life, these regions. But you also see, of course, in these regions, the human imprint. Johan Rockström spoke this morning about the Anthropocene, that people are now affecting all parts of the planet. So what signs do we see of the imprint? Maybe you can speak a bit to that as well, Lisa and Amelia, on how humans actually affect the oceans and the polar regions.
But what we see is also, of course, not being in the polar region myself, but being in a lot of beautiful places, but in closed, dark conference rooms. And I think what we see many times is that what's happened on land comes into the ocean. So when we talk about the challenges in ocean, on pollution and plastic and chemicals, it comes from land. So the life on land comes and rinses into the ocean. And it doesn't matter if it's a coastal area, because it comes with the water and the pathways and the lakes. So it's all interconnected. And that connectivity we will need to address.
Yeah, the effect is completely pervasive. It comes from the land, it comes from the air. I've visited the area east of Svalbard a number of times over the last 35 years, and it's really a great example of environmental change in action. 35 years ago, you needed an ice-breaking research vessel to get there, and even then, maybe Plan B had to be enacted every so often because of the ice conditions. Now, in the last 5 to 10 years, you can go there in an ordinary ship, and indeed, we have seen polar bears there swimming, and polar bears can swim a long way, but they can't swim forever, and their environment east of Svalbard has more or less disappeared in the time that I've been a scientist.
Do you have a personal experience of climate change? Climate change can seem as such a diffuse, difficult to grasp kind of issue, but you have a personal experience of it.
Yeah, I mean that's anecdotal, but we're scientists, and the statistics of sea ice cover in the Arctic absolutely back up that statement quantitatively.
What about the deep seas? Can you notice humans there? Something?
Yeah, so we tend to think of the deep seas as this sort of, extremely remote but also very pristine place. But unfortunately, that's not the truth. I think I've been on 16 expeditions now, and on nearly every single one, we've seen Olita, which is perhaps the easiest thing to notice, I guess. From a Spam can in the Mariana Trench to literally a plastic bag at the world's deepest point in our oceans. And it just, it reminds us that we leave our touch everywhere we go, even if we don't actually go there.
And it also shows, of course, when we do have plastics in the ocean, it's also the microplastic and the big plastic what we see, but that also tells us what else is going into the ocean. And we see in the pictures of the animals that it's a very easy way to communicate what's happening and to touch people. But behind that, there's also other huge problems. Emissions we don't see, chemicals we don't see. So of course we need to address the disability, but also link it into all the other challenges.
But whose responsibility is really the oceans? Because these are our global commons, we all depend on them, and they're everyone's and no one somehow. So who is responsible for this?
I guess we like to trust governments, because governments are accountable to the people in the nations and, of course, in the democracy. But we also see the lack of governments and enforcement and follow-up. And ocean is a vast resources, it's a space, it's an area where we have no rules and regulations in place, really. So we want to see governments, but I think the dialogue between governments and private sector and grassroots movements, everyone that have a stake in oceans, is everybody's responsibility as well as accountability to take care of the oceans. But that's also the challenge, because the high seas outside the sort of economic zones, half of the ocean is high seas, and we do not have all rules and regulations. So waiting for rules and regulations, where we want to move ahead and really having private sector taking the responsibilities. So not only that the person or the company have money and finance means go out and catch fish, for example, or governments that have the knowledge and technology to go out and feed the resources that actually belong to everyone, no matter where.
And what makes you hopeful then? Because I know you've worked a lot with partnerships for the oceans and trying to bring all of these stakeholders together. Are there signs of hope in addressing these challenges that we've just spoken about?
I think what previous panels have discussed is not only, of course, the trust in governments, but also how can we engage the grassroots movements, the people, and empowerment of the people, and how they can use technology together. And moving in an awareness and outreach.
Your microphone seems too bad, so maybe we can turn off that microphone and use this one.
Now maybe that's much better. It felt that I was under the ocean for a time. Just to emphasize my point, I think what's really is encouraging is the empowerment of the younger generation and the grassroots movements. And not only that, but the link to technology and the spread of technology and the tremendous amount on how those link knowledge and science and how to use it and push the governments to take action. Ask our politicians, you're accountable to the people. You have the responsibility, and we really demand change. That's what I think is a positive outlook.
Mm. And since we are at the Nobel Week Dialogue, I'd like to also talk a bit about the role of science, especially in this endeavor, because of course I'm also a scientist. We search for knowledge, and knowledge is really important. But is there more that we can do when we work in these particularly sensitive regions to really? I know you're both connected to also communicate about your findings. So can you say something about the role of science?
Yeah, I think that science has two roles. One, and most fundamentally, it is to understand and quantify the working of natural systems, of which the ocean and the ice that feeds into it is one. But it is certainly the case that needs to be communicated to, and I think everybody in this room realises this, and we're all trying to do that in a variety of different ways. And whether it's talking to governments and ministers of state or the UK Foreign Office on the one hand, or whether it's talking to a class of 5 to 6 year olds in our local school. And actually I think that in a way is a particular challenge which I very much relish. The way that the young children really embrace science and really embrace things like the oceans and things like the polar regions is really very wonderful. And if we can do more of that in schools, I think, and project the environment and environmental status change through curricula, because curricula and the way that curricula develop is really important to getting these messages out to people from 5 to 18.
To build the next generation of ocean stewards.
Exactly.
And I think scientists have been, traditionally terrible communicators, mostly. And thankfully, I think that status quo is changing. I mean, not everybody was, but it needs to change, and really quickly, because we need to be communicating what we know. We're the experts, and we need to try to, not only, as Julia just said, speak to policymakers so that we can have science-based, rigorous science-based regulations put in place for our oceans, but also to the public, whether it is kids or whether it is, your mom at home, just so that we can galvanize change in behavior, as Lisa Emilia was saying earlier.
Something we've tried at the Stockholm Resilience Center, where I work, is also to connect with business leaders of businesses who really depend on the ocean, and to bring them together and showing them the facts that if they continue business as usual, there will be no business in 10, 15 years, but then also to provide a platform for them to discuss how they can operate in a different way. I think you've worked a lot with the private sector as well, Lisa Emilia.
So one of the goals that we're talking about is the 17th, which is public-private partnership. And I think the dialogue between the public and private, and how you find a win-win situation where we both want to have the same thing, that's how we kind of can achieve not only the ocean goal, but all the goals on the sustainability that Johan Rockström also talked about. It's not just one goal, but how can we, in a sort of social, collectively work together. That's how the private sector needs to be involved. And we are currently working with the private sector on so many different angles. And they want to be part of the solution. And we do have leaders, and I think we need to join the leaders together to move the action. And also explain why the governments need to be accountable, but also why the private sector needs to go ahead and showcase for other private sector that this is a thing to do, and we need to be in there together.
Just some final words then, because we're soon out of time, and I want to go back into the audience again, because you apparently all ate something from the ocean and have a personal relationship to it, so I'm sure you're into to also support the oceans now that we know how much we depend on it, so or on them. So what would be something that people in this room can do for the oceans?
Well, first of all, I think we want to be inquisitive. We want to make sure that we ask questions, and as far as we can, we want to understand what is going on in the oceans, and in my case, the icy world, and how those two interact together. And I think to build up a knowledge base, if one can, allows us then to understand and then to advocate in the most effective way. So I think it's understanding and then advocacy.
So learning more about the oceans. Thank you.
I think we should think about how we are living our life, who's taking care of the life that we lived, meaning the waste and the garbage, plastic, one of them, and what does that bring and how does it come into the ocean. So closing the loop and really start to rethink what are our residents from the consumption that we use.
Again, this fact that the things that we do from land end up in the ocean, so making sure that we bring that back into our system.
I guess my answer is a combination of both. We need to A, gather the knowledge, B, use that personally to become better consumers, more responsible consumers. And finally, we need to learn, I guess, not just from the science, but also then take that knowledge that we gain and teach others, inspire others. Because once you know something, you can't unknow it. And I think that's when behavior is really going to change.
Thank you so much. Thank you, everyone.
Thank you very much indeed. Thank you. Sorry about the microphone. Thank you, Lisa. You know, I found that microphone in this bucket. I'd been rather hoping it was a nice cold beer for later, or some champagne, but I suppose a microphone is more useful, so. The theme of the role of science came up in that panel, and we're very privileged to have a large number of Nobel laureates at our dialogue today, but of course there are some other laureates in town this week, the 2018 Nobel Prize laureates, and we asked a couple of them for their thoughts on the role of science, and we have a short video.
Science is the most important thing that humans have ever invented. And really, what I mean by that is broader than just science. It's really intellectual inquiry. So the work of novelists, the work in the humanities, the work in the sciences, where economics sits a little bit in between the hard sciences, the humanities, and literature. All of that work is the most important thing humans have ever invented. This community of people who trade ideas, this community of people who write things down so that they can share ideas with each other, this community where they have norms that celebrate disagreement, open, honest disagreement in the pursuit of an eventual consensus that's more precise than any one person could have come to on his or her own.
I think everybody needs to know something about science and engineering. Maybe they don't go and get a degree in it, but we need a scientifically literate population. Science and technology is the future. It's the future of the planet. Without science and technology, we won't feed 10 billion people. We won't provide water. We won't have cities that are even worth living in. It's science and technology, so everybody has to do it. And most certainly women are going to play a huge role in the future of science and technology because that's where 50% of the best minds are.
So now we're going to leave our planet and head off to Mars. And to take us there, I'm very pleased to welcome Roberto Orosei.
It's a pleasure and an honor to be here today. So we will be talking about Mars and what has to do Mars with Earth. Well, if I showed you this picture, and I didn't tell you this was taken on Mars by the Curiosity rover, you would think we are, except for the reddish color of the sky, somewhere in the, well, southwestern United States maybe, or even Sahara Desert. So Mars looks a lot like Earth, except for the lack of life. The problem is that Mars is actually much harsher than the Earth. What we see here in this picture is not what it feels to be like on Mars. Temperature on average is well below zero, and at the poles reaches minus 100 centigrades. Air is very thin, the atmosphere is made of CO2, and it's less than 1% of the pressure we experience on Earth. Also, this is the very driest desert one can think of. If all the humidity of Mars could precipitate at once, it would form a layer no more than 10 microns thick. So it's drier than any desert of Earth could ever be. Now, there are signs that things were very different in the past. And this is the kind of things that has given us clues about the distant past of Mars. In place, we see river beds, we see lakes, but they are all dry. This one in particular is called an outflow channel. It has been probably produced by a single catastrophic event of water release, the like of which current Earth has never seen. So Mars in the past had different climate. It had to have a different climate because otherwise water could not exist on its surface. But for this to happen, it took a different atmosphere, made of CO2, but much denser than the one that exists today, and which would form and cause a beneficial, this time, greenhouse effect, capable of raising temperature above the melting point of water. However, things changed pretty soon. Mars, being much smaller than the Earth, having a weaker gravitational pull, it could retain its atmosphere over the ages. Also, Mars lost its magnetic field very early in its history, and our magnetic field protects our atmosphere from erosion by the solar wind, the flux of particles that constantly is emitted by the sun and hits us. But without a magnetic field, the process of atmospheric loss accelerated. Finally, all this was compounded by the ceasing, the decay of volcanic activity to almost negligible level. And volcanic activity is important both on Earth and on Mars to provide gases to the atmosphere as well as a source of heat. So this led to the early demise of Mars, but there is still water there in the polar caps. But this is not enough to explain all the water features that we see. What we think, and what has been already observed, is that there is also ice in the ground on Mars. But the problem is we don't know how much and how deep it's there. Fact is that Mars is still hot in its interior, and as you go deeper, temperature increases, so that if ice reaches deep enough, there will be a point at which ice will melt because temperature has increased to 0 centigrades. So looking for water on Mars, liquid water on Mars today, means looking for subsurface water. This is a search that has been going on, at least if we are talking about stable water, of course. This search has been going on for a long time, and luckily only this year we have been able to show that there is a particular place in the South Pole of Mars where under 1.5 kilometers of ice you have what seems to be liquid water. It has been discovered by a radar called MARSIS aboard the European spacecraft Mars Express, and basically it's similar to the radars that are used on Earth to detect subglacial lakes in places like Antarctica. So what we have found here is liquid water but however this liquid water is not at 0 centigrades. There are indications that this water is saturated with salts, So it's not the kind of water you want to see coming out of your tap. But still, these salts being very likely perchlorate salts, there are bacteria on Earth that could use such salts for their own metabolism. So the discovery of this water, for the first time on Mars, presents us with a real possibility that there is an environment safe for life on Mars where existing life forms on Earth would be able to survive. And if Mars in the past, in its temperate age, has developed life, maybe life is still there waiting for us to discover. Thank you.
Thank you, Roberta. What an exciting prospect. Now, to help you continue in this exploration of water on Mars and other places out there in the solar system, please may I also welcome your moderator, Julian Zirath, Stefan Hell, and John Gertzinger.
So I'd like to welcome you all to this panel, Water on Mars. And Roberto, thank you for setting the stage for us all. And I'm joined here by Stefan and John. And I think for the next 20 minutes, we want to have a really lively dialogue and discussion on topics that are really related to water on Mars and how that influences on our own planet. So Stefan, I want to start with you. You've spent most of your life behind the lens of a microscope. So why is it important for us to look for water on other planets?
Well, I think there are two fundamental reasons from my viewpoint, and one is the simple fact that water is a very abundant substance in the universe, I'd say the second most abundant substance. And so we need to understand, where does it come from actually? Was it made in a single event? How is it distributed? Has it changed? How was it formed on Earth or not formed? Does it come from somewhere? That's one of the reasons. The second reason is, of course, that life as we know it, at least, requires liquid water. And we need to understand, has there been similar events outside this Earth as well?
So I'm going to go, was it a surprise, the discovery of water on Mars?
I think every time we have a vehicle that looks down at the surface of Mars from orbit, or a lander or a rover that then confirms that there was once water on the surface of Mars, it's always a great discovery. It just seems so improbable based on just looking at the planet today.
So Roberto, you talked a little bit about the existence of life. So what do we need for the emergence of life from planets like Mars or other ecoplanets? And what's an ecoplanet, by the way?
Well, I think that the fair answer is that we don't know. We are not able to create life in the lab. We know that the elements that are necessary to life are essentially, life as we know it, is liquid water and a certain amount of carbon, nitrogen, oxygen, and other elements. And we need a source of energy, but we don't know if this is enough to start the process. We don't know.
So what do we need for a habitable life on a planet like Mars? We're basically putting a lot of efforts into making expeditions outside of this planet ourselves. What do you think we need for a habitable life there? I mean, obviously water is going to be one of them, because that's the theme of this whole meeting.
Well, looking for water on Mars and looking for signs of extant or extinct life is to me connected to a more grander question, which is life common in the universe? As I just said, on Earth, it's difficult to understand the whole entire process leading from inorganic Earth to the simplest form of life. And maybe exploring Mars is a way to bypass our ignorance and go directly for the answer. If we were to find that life exists or existed on Mars, we would have to conclude that life occurs whenever there are the conditions that we think are necessary, that there is no special happening required for that. And we would be led to conclude also that life must be abundant in the universe.
Do you have a sense of how much water is there under the surface of Mars?
You know, I think that as Roberto was saying during his presentation, we really know now that with a high degree of certainty there was once a lot more water than exists now, and for reasons that he described, the atmosphere was lost. And really the trick is when you go go through the architecture of building a mission like the Curiosity rover and pick a landing site, you have to hope that what you will find is immediately a place where there was once water that was present, that you'll be able to use your analytical instruments to look for the key elements of life: carbon, hydrogen, nitrogen, phosphorus, sulfur, and we found all those.
How do you read that?
Well, so you have instruments that will then give you an inventory of those elements, but then also tell you the minerals that they're in. And that's very important because that tells you about the redox, it's iron in the +2 state or the +3 state. Because microorganisms, in order to survive and be habitable, need to be able to work with those electron flows.
I mean, you're a physicist. What kind of tools do you think we're going to need?
Well, possibly a microscope to look at the details, but I have a question for you. I mean, you mentioned that there was an atmosphere on Mars probably, and there was water on Mars most likely. So why did the water disappear, or what are the conditions actually for holding the water on a certain planet?
I think that from what we know today, most of the water on Mars has left with the atmosphere. So as the atmosphere was being dragged away and lost in space, even water in there was lost. But again, the big possibility is that a lot of water is still waiting for us subsurface, and perhaps the liquid water found under the core cap is just the beginning. It's deeper into the crust in areas which are more difficult to probe with the radar. Ice is very transparent to radar waves. Could have more liquid water and a real environment. This is possible.
We started a little bit with Stefan, why look? And I would just maybe want to ask you maybe to discuss why is it important to know this, and how is it important for us to understand more about ourselves from understanding water on Mars? Can we learn anything about our own planet from that study? John, go ahead.
I always like to say to my students that if we never find life on Mars, you can still make lemonade out of lemons, because it's not a sister, but it's a close cousin in terms of its earliest first billion years. And there may be remnants of prebiotic compounds that were important to leading to the evolution of life on Earth that are no longer preserved on Earth because plate tectonics turns everything over. But Mars is like in a state of suspended animation, maybe with the very beginning materials.
That's for you? What are we going to learn about ourselves from understanding water on Mars?
Well, again, maybe I'm going a bit off the topic here, but again, this to me is tied to the perception of our place in the order of things. And knowing about life and its occurrence in the universe, to me, will have such a cultural and philosophical impact on our lives that cannot be compared to anything we have discovered before. If we just think the fact that by moving the center of the universe from the Earth to the Sun has led essentially to modern democracy, because it was the telling blow to the theocratic oppression system born out of feudalism. Let's imagine, nobody can imagine fully what would happen if we were to find life on Earth, or outside the Earth, or not, actually.
That's from you?
Well, I think it's very important to realize that it might be very hard to have life on other planets. And I think this search for liquid water and for life on other planets, and the difficulties that you have to take, just prove that Earth, in a way, is very special. And so, in the end, we have to make sure that the Earth is preserved, and I think the search for life on other planets will tell us how precious actually our Earth is.
We talked a little bit, because we did some prep, but extraterrestrial intelligence, and I think maybe you might have brought that up in the early discussions. Maybe you can say a few words about that, because in the search for water, we're also looking for new knowledge and intelligence, but talk a little bit about extraterrestrial intelligence.
Well, the search so far has been
what is it, first of all?
Search for extraterrestrial intelligence. This essentially means looking for signals that are not natural, that are artificial in nature, coming from the rest of the universe. This has been done using radio telescopes, because radio waves seem to be a very convenient vehicle for information across stellar distances, but the search so far has been fruitless. However, our efforts compared to the magnitude of the task have been very limited. And in fact, by accounting for the area of space and the band of frequencies and the way in which the signal can be modulated, all our efforts amount to collecting a single glass of water from the ocean and expecting to find a fish there.
Most of us have enough trouble communicating with each other, and now we want to communicate with the rest of our solar system. But can we use water for that? Is there any thought about that?
Well, water is for sure, at least very likely the basis of life everywhere in the universe. There are several factors for that. The fact that it is a very abundant compound, the fact that it has thermal and physical properties that are very favorable for the kind of chemistry life requires, the fact that it remains liquid at a range of temperatures at which carbon, compounds remain stable. So all of these, and carbon being a very common compound in the universe as well. So life seems to have, a very reasonable blueprint for life would include water and carbon. So it's difficult to think out of that, although of course it's possible.
Well, I want to take a little bit of time now just to kind of wrap up and give each of you an opportunity to just share with us what you hope for going forward. And I thought maybe I'd start with you, John. What do you hope for because of this kind of research and this kind of new insight?
Yeah, I think if I pick up on that last theme a little bit, if you take a glass of seawater and look for microorganisms, you're going to find them every time. And earlier in the session today, somebody said every second breath of air comes from the ocean. Those won't be from higher organisms, those are from microorganisms. And so what I hope for is that we are able to find the funding and continue to build the James Webb Space Telescope to aim at extrasolar planets and look for in the composition of their atmosphere, look for oxygen. Because if you looked at Earth from another solar system, in addition to being able to look at its size, mass, density, and all those fundamental physical variables, the minute you looked at its atmosphere with a spectrometer, you would see oxygen. It's a fundamental property of the Earth that belongs to life. So my hope is that someday we may discover an exoplanet with an oxygen-rich atmosphere.
Okay, that would be really exciting. How about you?
Well, I subscribe to what Dr. Grotzinger has said. I would also add that to me, space exploration for this kind of endeavor would be a great opportunity for giving us hope, giving us a sense of belonging and a perspective for the future. I think that having been born in the years of the first man on the moon shaped my perception of the world and directed by my life. And this sense of destiny, of having something important to do, seems to have been completely lost now. And this is something I'm really missing.
Were you there?
I think the search for water on other planets is purely curiosity-driven science, and I like it very much. And I very much hope that something surprising comes out that no one expects, and tells how fun science is, and of course how many insights, fundamental insights, as you mentioned, science can give. And secondly, of course, I hope very much that people understand the value of the environment that we have and the uniqueness that we have, that we really have to work hard to sort out our conflicts on this planet in order to keep it habitable for us.
So we hear a lot about blue sky research, and this is probably going to be blue water research. And
Absolutely.
So the final thing I want to bring up, though, is a lot of the people here are young, aspiring chemists, physicists, biomedical researchers, and also interested in the culture. But what advice would you give to young people that are really about to embark upon their careers based on the kinds of insight that you have? I'll start with you. You teach a lot of students, so what advice about?
It's simple. I think you just have to pursue the things you love. And then if you do that, good things will happen.
Okay. How about you?
Read and keep reading.
Read and keep reading.
I'm not good at that. I think passion for science, I fully agree. This is very, very important. And because if you're passionate about what you do, you overcome all of the hardships because it doesn't feel hard. And
Good advices.
Yeah.
And we do have a spectrum of people that are really interested in policy, and we heard a lot about trying to understand how politicians can help us in terms of our issues around water. When we think about looking for water on other planets and exoplanets, who's going to police that? Will we need to police that? Or can I just, create the next system to go up there? How is that going to be managed? Because it's really, we're dealing a lot with our own planet. Can we learn from this?
Yeah, that's right. And water and climate change. That's in the conversation.
5 seconds.
And there's diseases, many killers like cholera, loom in the background.
Excellent.
No.
Operator. Oh, yan. Ito po ang isa sa mga Pilipino natin mga kasama po dito. At ito mga bayani po natin ngayon. Ayan. Layo-layo ng binyahe ngayon. Nagtitinda ko ng halo-halo. Halo-halo, asorbetes. Yan, halo-halo. Ganito po ang kagagaling ng mga Pilipino. Ano-ano mga trabaho pero marangal. Ayan. Nagpapausok po siya ngayon. Ayan, kita-kita nyo ito. Pausok. Ayan. Ito po siya. Brad, tiga saan ka sa atin ulit sa Pilipinas?
Davao.
Davao. Nako, so batiin mo naman yung mga kamag-anak mo sa Davao.
May mga kamag-anak ko dyan sa Davao, sa Leyte.
Mga pinagkakautangan, yun daw mga sa Pasko, sa kanilang daw. Sinsilyo na lang.
Halo-halo gusto nyo?
Ayun. Ayan.
Lalagyan natin mainit na tubig para mag-effect yung mga dry ice.
O, kita nyo, may science pa yan. O. Ganyan yung katatalino mga Pilipino. Ayan po. Ayan.
Mainit na tubig.
Ito mo nga.
He probably has the coolest job out I think she was there for the rest of the day. Come on, guys.
They would answer when they wanted to answer.
Where's the bubble?
Oh, God.
Roberto Orsi. And I thought what we would do is just start off by talking a little bit about what our interests are with life elsewhere, and make sure we have plenty of time to get questions from y'all, and we'll just sort of take it from there. So I think let's start off with Diva. Let's tell us about life on Earth in strange places.
Yeah, so I guess...
At least we know we have it here.
Elsewhere doesn't necessarily mean, you know, other planets. I guess up until, you know, 2 centuries ago, we had no idea that there was life in the deep oceans. In fact, most people thought that it was this anoxic place where life could not survive, and it was just a sort of barren desert. But in fact, we now know, as I said in my talk, that it's one of the most biodiverse places on the planet. And it just shows that, you know, we really do need to keep looking, because we never know what we're going to find, and that could provide us clues to life in other places, which I'm sure the panelists will.
And when you're looking, how do you do that?
Variety of ways. We tend to use a suite of equipment, from the very low-tech, such as trawls, you know, throw a net off the back and see what we pull up, to very high-tech equipment, things like remotely operated vehicles, which are robots, which are our eyes, our ears, and our hands on the deep sea floor, and also autonomous underwater vehicles, as we were talking about at lunch, which are the future. You know, we just send them down there and they do what they need to without us needing to actually be there with them, controlling them. And of course, the best part are submersibles, which are used much less now. But when we actually ourselves get to go down into the deep ocean to see the amazing life down there.
Have you ever been in the Alvin?
I have not been in Alvin, but I've been in the Japanese version, which is the Shinkai 6500, and we did some dives on hydrothermal vents in the Kama Trench, which was pretty amazing.
Was it scary?
You're scared for the first 5-10 seconds as you're hitting the water, because you're like, well, if something goes wrong down there, no one is coming for us. But once you start descending and you start looking out the porthole, and there's just the most amazing bioluminescence, like shooting past the window, like the most amazing firework display you've ever seen, you just forget all about it. And then, of course, because there are only 2 or 3 people in the submersible, you have a shopping list of tasks you need to get through, and so you immediately kick into, these are the things I have to do, let's just make the most of it.
Cool. Randy, you have some experience with thinking about the history of life on Earth.
Well, I can tell you that first, the unusual life forms that I have encountered in much of my career come from the fact that I'm a professor at the University of California, Berkeley, and we have many strange life forms there.
Oh, you haven't been to Caltech lately.
My work is mainly, though, on normal organisms, on microorganisms. So I've worked on how cells grow and divide, how cell membranes get put together. So thinking about that from an evolutionary perspective as relates to our discussion, microbial life evolved on Earth probably just after water appeared on Earth, as much as 3.8 billion years ago. That was in the form of either bacteria or archaea, 2 of the 2 large microbial forms of life. But eukaryotes emerged probably 1 billion or more years after that. Eukaryotes are characterized as often single-cell organisms or multicellular organisms that have compartments within the cell. Typically the nucleus, the chromosomes are housed in the nucleus. That's distinct from archaea and bacteria. But they also have other intracellular organelles, some of which evolved by an endosymbiont relationship with microorganisms. The mitochondria and chloroplasts coming from photosynthetic bacteria, most likely, probably 2 or more billion years ago. So in thinking about life emerging elsewhere in the universe, I'm virtually certain, I'd be willing to bet almost anything on it, that there is life out there. I think the universe is likely teeming with life. And I think we can rely in part on what we've learned about microbial life forms on Earth to guide us in looking for not only the environments, but the molecular signatures of life. And so I'd like to speculate on that as our conversation goes on.
Okay, well, we can do that in a minute. Before we move on to Roberto, one question would be, when did oxygenic photosynthesis evolve? And is it possible that on another planet somewhere that could have been the first thing to happen? We tend to think, based on Earth experience, it happened later.
Yeah. Well, interesting you should ask that. In preparing for these remarks, I relied on my trusty partner, Professor Sabia Merchant, who's an expert in microbial photosynthesis, who gave me the following number from this conversation. The great oxidation event on Earth occurred maybe 2.3 billion years ago. And so oxygenic photosynthesis actually preceded the accumulation of oxygen in the atmosphere, perhaps by as much as 500 million years prior to the accumulation of large quantities of oxygen. But even before then, hydrogen was a reductant in the first forms of photosynthesis, and that occurred virtually at the same time as water appeared on the Earth, as much as 3.8 billion years ago. So in looking for photosynthesis as a signature of life elsewhere, one is almost certain to be able to discover light-absorbing molecules that will signify life elsewhere as a very early marker of the emergence of life, even just after the production or the accumulation of water. I think it's almost certain that as exoplanets are now being discovered, and even those with poor atmospheres, as long as we can detect water on the surface of an exoplanet, I think I will predict that within our lifetime we will see biological molecules that can be detected from great distance by very accurate spectroscopic techniques.
That's a great segue for Roberto to tell us about exoplanets and what are your thoughts about their relationship to our solar system?
Yeah. Well, when I was a student, exoplanets were just a possibility. They were mentioned as something we ought to discover, but the first announcement came in 93, I think. And since then, however, the rate of discovery has increased dramatically. And nowadays we have a catalog of perhaps more than 3,000 exoplanets around stars in our vicinity. And they have mostly been discovered by the Kepler mission in space. The interesting thing is that solar systems other than ours are very different. And it was a shocking discovery to see that in the place around the star, the distance around the star, where one needs to have planets like our own, terrestrial rocky planets, to have the possibility for life to develop, there were instead giant planets made of gas, which are like Jupiter or even larger. And that was quite a surprise at first because, well, of course, these planets being big were easier to discover, but they were quite, they would have scattered away, thrown into space or into the sun, their sun, any other smaller planet that was orbiting a comparable distance. So it seemed like the engineering of planetary system formation was just getting in the way of having places for life to develop. Later on, it was also realized that these giant planets have moons, and in fact these moons have a solid surface. If we work by analogy with our solar system, and in fact you might have noticed that Pandora, the one in Avatar, is the moon of a giant planet. But and even after that, as information knowledge continued to accumulate, it was found that in general, however, our solar system is atypical for the lack of planets of mass intermediate between that of the Earth and that of Neptune, which in fact turn out to be the most abundant bodies outside the solar system, in exoplanet, the most abundant type of exoplanet. So there are certainly things we don't know about how planets form in the first place, let alone develop to harbor life. And this is very fascinating at the moment. However, current measurements have provided a list of maybe a dozen, 15 or so planets that have a mass comparable to that of the Earth and are in what is called the, they call it the Goldilocks zone. Either not too cold, not too hot. Okay? So the distance from their stars where climate would be reasonable, surface temperature would be reasonable for life to develop as we know it. And so out of something like 3,000 planets, 15 planets is 0.5%, it's not that much. But if you extrapolate to the entire galaxy, which is about 100 billion stars, and if we make the assumption, which is more or less true, of about, on average, 1 planet per star, this goes up to a whopping 500 million inhabitable planets in our galaxy alone. And this is something to think about.
What's your feeling about upcoming astronomy missions like JWST and their ability to image M dwarfs and maybe even L dwarf and the planets associated with that, because it's a different kind of a star system?
Well, of course, it would be an amazing giant step, an amazing step forward in the exploration, but I am not close enough to this field of research to be sure of if this will be mostly an increment of the quantity of planets we are able to detect in terms of threshold of detectability, or if there will be also the capability to do what is now almost impossible to do, which is spectroscopy from Earth. And in fact, the only information we have about the atmosphere of exoplanets concerns the giant gas planets where we usually don't envision the possibility for life to exist. So what I can tell is that we should really stay tuned from the moment in which someone will be able to tell, oh, wait, there's an atmosphere without oxygen in it. At that moment, well, that would be the big leap forward, because apparently, well, oxygen is considered one of the telltale signs of life, of the existence of life, in that oxygen usually doesn't form molecular oxygen in the cosmos. The oxygen usually combines with hydrogen, which is the most common chemical species in the universe, to form water. So seeing oxygen in an atmosphere, and as it was mentioned before, oxygen was produced by photosynthesis, is in fact the sign for photosynthesis to exist. And there have been thoughts about pathway to have molecular oxygen in atmosphere without life. But this would be possible mostly if you had a planet which is covered by water ice, for example, but also bombarded heavily by ultraviolet radiation. That would cause the dissociation of water and allow the recombination to form molecular oxygen. That would be a way. But this seems, let's say, a complex set of circumstances for that to happen very often in space.
Could that happen to a place like Europa?
If it got closer to the sun, yes. In fact, this is the hypothesis that I was mentioning, the planets of mass intermediate, of an intermediate mass between that of the Earth and of Neptune. And those planets, especially going towards the gas giant planets, if they happen to move close to their stars, solar wind from the start, depending on the type of stars, of course, could wipe away the hydrogen envelope of the planet and leave the ice and rocky core exposed. But the ice in these kind of planets would be much more abundant than on Earth, and would in fact constitute an outer layer which would cover, which would extend for a significant fraction of the radius of the planet. And you would have thus an ocean world in which you would have almost limitless quantity of water which could be continually exposed to ultraviolet radiation, and then over time this could build up an oxygen atmosphere.
Right. I think let's take a break there and see if there's any questions from the audience.
Don't be shy.
This might sound like a naive question, but I'm curious about when you're down there when it's pitch black normally, and then you come with your strong lights to film it. What happens with the species down there? Did you show these fish with huge eyes? I mean, will it have some impact on
That's a
on
great
their...
question. So, first of all, a lot of species in the deep sea do not have eyes because there's no need for it. But some do, and that's, I guess, to detect bioluminescence and other things. But unfortunately, you know, even though scientists go down into the deep sea and go onto other planets with the best intentions, we still have an impact, of course. And those lights likely do, I mean, if you were trapped in a dark room for your entire life and then someone shone one of the brightest lights in your eyes, it'd probably maim you in a very serious way. So a lot of these animals, unfortunately, are left probably blinded. But yeah, we're not sure about that. But there are a lot of them, and we, you know, it's for the greater good.
Hi, I would like to ask about the Fermi paradox, where, as you mentioned, there are a lot of possibilities for life to happen through emergence. And what role does water play in like analyzing and saying that, oh, this planet has life? Thank you.
Life on Earth depends absolutely on water, but that's not to say that another form of life could emerge independent of water. But as we know it here, water is the solvent that makes every microorganism survive. Catalytic reactions depend upon water. The protein and nucleic acid molecules within cells are bathed in water. The bonds that hold these molecules together often come from water. The hydrogen weak bonds, non-covalent bonds, all are the result of water interacting with biological molecules. But I'm not in a position to speculate on what could exist outside of water as the universal solvent that we rely on.
The first part of your question was about the Fermi paradox, however. Just a couple of words is, I think that it's attributed to Fermi, but it was not really his wordings. But he said, if they exist, if aliens exist outside the Earth, why aren't they here? And I read a recent paper saying that we might be among the earliest planets harboring life, simply because to have a planet you need to have heavy elements in a sufficient quantity, and this means that you have to have several generations of star grow, let's say produce heavier elements in their interior, explode and disseminate them in the universe. So to have life, to have intelligent life, which took several billion years of evolution, well, you have to be patient. But even to build planets in the first place, you have to be patient too. So we might be the first, or among the first in our galactic neighborhood, intelligent species.
What about these? So what about these organisms that don't use sunlight to produce their own energy or to get energy? So could a planet be inhabited by those, is there something different about them that could say anything about how life forms or what the prerequisites are for those? Like, for example, some organisms that have been found very deep in the ocean that have a very much longer life cycle than, I guess, ours. Yeah.
Want to jump in for chemosynthesis?
Well, one thing that is usually accepted in exobiology is that as far as we limit ourselves to life forms based on carbon and water as a solvent, probably terrestrial life fills the entire envelope of potential habitats. So this is plausible as an hypothesis because life had a lot of time to adapt, and the most extreme environments are inhabited by the simplest life forms, unicellular organisms. So usually it's postulated that the limits of life elsewhere are the limits of life on Earth, as long, again, as you take water and carbon as the blueprint for life. And this means that you are able to live between minus 30 and 120 centigrades, if I remember correctly, which is not for us, for sure, but for simpler organisms, and that you can live at very high pressures deep underground. And you can also live in salt-saturated water and even use those salts to produce your energy. So life can do a lot of things. And in fact, studying life in extreme environments, this is essentially the basis for understanding life outside the Earth.
That's actually the point that I was going to touch on. It is important to look outwards for life, obviously, but we need to remember to look inwards as well, because we have these environments where the most primitive or relatives of the most primitive life forms exist, for instance, the hydrothermal vents and methane seeps and so on, that have very similar conditions to where potentially life may have formed initially. And so we need to remember to look inwards at our own oceans to be able to have analogues for those elsewhere.
And they're a lot more accessible.
Yes, absolutely. I mean, they're still difficult to get
but
to.
But not so accessible.
Yeah, exactly.
Hi, I am Anant and I'm from India. So I want to talk about one thing. So it's really very beautiful and always very exciting to discover the life which is in the ocean. But in a way, I also feel like when we are discovering those technologies, the ways, it's usually convenient for us. But when but for the lives down there, they are harming. Our technologies are harming. So like after a couple of years, we just came to know like whatever we discovered, they are actually harming them. So I really hope that for the next like innovations or technologies, I hope they're pretty sustainable, not just for us, but for them as well. So we don't extinct the beautiful lives down there.
Yeah, I think that's a great point. While, I mean, of course, for instance, as we mentioned with the lights, we do harm animals down there in various ways, but it's still in a really minuscule way. Where I think we need to be careful is where exploitation comes in, you know, where industry comes in. And of course, while that is incredibly useful in a lot of ways, for instance, in the deep ocean, we're beginning to think about extractive industries, such as for minerals and oil and gas and so on. And so we need to keep doing the science. Even though it's a little bit harmful, we need that science to inform how we manage things, because we can only really effectively manage something and make sure it doesn't go extinct by understanding it, right?
Yeah, there's a question here.
Okay, so you mentioned the possibility of finding liquid water on Mars, for instance, and therefore perhaps living creatures. What is the legislation how is the legislation going to influence your work and the discoveries that you're going to make? Is there something that's going to block you somehow?
Well, legislation, we made a passing reference to that I think that the law for the moon, which will probably provide let's say the first term of paragon for future developments in planetary exploration, is that the moon doesn't belong to anybody. So, and this is similar to Antarctica essentially.
And the oceans.
And the oceans. So if we keep going like this, I feel quite confident we could avoid making tragic mistakes. But there seems to be a trend in changing as the developments of systems for, say, mining asteroids continue, and there has been a piece of legislation passed under the Obama administration, if I remember correctly, that somehow circumvents this this law. Something that more or less says that yes, you cannot own, say, an asteroid, but you can exploit it, and this is. I've not really gone into the implications and the details of that, but this is something to keep an eye upon. There is interest, of course, economic interest behind this, and some administrations are already making their steps to be, let's say, hit the ground running wherever the opportunity presents itself. So we also must do the same if we are interested in ensuring that space remains an opportunity for everybody.
Hi. So we have talked about life in general, but I was wondering, what about intelligent life? Because we know that you said it's very easy for life to develop even within our galaxy, but what's your take on intelligent life? That seems to be much harder, right?
I think that's a very hard question to answer with any certainty. We can talk about more complex forms of life after the bacteria and archaeal species. Eukaryotes, as I said, evolved maybe about 2 billion years ago. And from that, more complex life forms evolved over the next billion years. Plant life, animal life. But intelligent life required a leap beyond what we can really understand in terms of typical evolutionary studies. I think intelligent life in the universe, that's assuming there's intelligent life on Earth, will be much more difficult to predict. I mean, if it exists and there's some ability to communicate over long distances, then we'll find it out. But looking for it deliberately from where we stand, I think, will be extraordinarily difficult.
Yeah, if I could just add to that a little bit. One of the greatest events in Earth history is the origin of animals. And if you invent life 3.8 billion years ago, we have records of it that are 3.5 billion years old, and then nothing happens for billions of years. And then literally in a period of time that took no more than 5, maybe 10 million years, you invent every phylum of organism that's on the planet today, plus a few more that went extinct at the Permo-Triassic boundary. And what is that magic? We still don't know what that is, let alone what Randy was saying, get to the intelligent part. So it seems that, at least for Earth, once you invent microorganisms, they're really happy. They're not forced to evolve.
But I think it is inevitable,
yeah,
in the conditions that we've had, that more complex life forms will emerge from microorganisms, given enough time. But intelligent life, that's not certain, I don't think.
So this is actually a question for Diva. Like, there's a lot of research towards life on Mars and water and everything, and technologies that can change our life in the future. But do you think that deep down in the ocean, is there something that can really affect Earth, in a major way?
Absolutely. So I can give you so many examples, but some ones that come to mind. For instance, there are minerals down in the ocean, which is now one of the emerging issues to do with ocean regulation. Deep sea mining is becoming a potential extractive activity, and the metals down there occur in such high concentrations and are so valuable as a result that they're potentially what is going to power the renewable energy that we need to move us away from climate change. So that's one of the big drivers of deep sea mining in the future. But to give you a more tangible example, because of climate change, we're now trying to limit our activities, our energy use, and so on. So we're washing our clothes at lower temperatures, right? So some of those enzymes which were used in those detergents actually came from the deep ocean originally. Because of course down in the deep sea, the temperatures down there are near freezing, and they're accustomed
to working at their maximum output at those freezing temperatures. And so you use those to potentially wash our clothes and make them clean at lower temperatures. And that's just one of the examples. I mean, one of the biggest potential issues we're facing in the future is antibiotic resistance. Maybe there's an antibiotic down there that could potentially help us.
Okay, I think we just have a few minutes left, so we'll maybe just summarize by some last thoughts. I'll pick it up and throw it right back to Diva. You know, we get so caught up in the exploration of space, that this great unknown, but how much of the ocean do we really understand, the deep ocean?
Absolutely, and again, it's about looking inwards. Yes, exploring space is absolutely incredible and gives us context for our planet. But we were talking at lunch, and less than 2% of our deep sea floor has ever been seen, ever been imaged, and that's astounding. We have more high-resolution maps of Mars, Venus, and the Moon than we do our own seafloor. And 1/10 of the animals in the ocean have names. The other 9/10 do not. In fact, the other 7/10 of them have not even been found yet. So if we're talking about life elsewhere, we really do need to remember to look right here.
I think looking inward, it's interesting to note that most of the life forms that one can examine and look at on Earth cannot actually be cultivated. Even most of the microbial forms, if you take a sample of seawater or a sample of soil and attempt to cultivate the microorganisms, grow them into colonies on a petri plate, most of them aren't sustained because we don't know the nutritional conditions that allow them to grow. They can be detected, however, because of the power of DNA sequence analysis. So you can detect in ocean water some billions of virus particles of unknown origin that are there that cannot be actually replicated in a laboratory, but by sequencing them you can know them. So I think the most exciting question that one might be able to answer going forward, just looking within, would be to see if one could detect organisms of a completely independent evolutionary origin, ones that are formed on the basis of something other than the traditional 4 bases of DNA. If one could find a way of doing that, organisms that exist on Earth, that would have a very powerful message to us about how life began and how it could evolve somewhere else.
Roberto.
I wouldn't add much to that. Exactly. Well, it's only, well, there is only one thing we have been talking about, which is life based on a different chemistry. And maybe we might mention Titan, in which, so 10 times as distant from the sun, more distant from the sun than the Earth. Titan is an icy moon of Saturn, in which there are rivers and lakes and seas of liquid methane, which is a solvent and is also organic, so there's a lot of carbon there, hydrogen, oxygen, and so forth. And so nobody has an idea of the kind of life that could develop there, but the ingredients for life as we know it are there. And so far there have been only very primitive, I would say, attempts at modeling that, but this is in a completely unexplored world in terms of chemistry. The only thing I know that has been accomplished, and actually through computer modeling, because doing experiments at minus 180 Celsius is quite complex, is that to develop something that would behave like a cellular membrane. So the chemistry that takes place in the atmosphere of Titan, thanks to ultraviolet radiation and the presence of hydrogen and nitrogen, could produce a molecule based on these substances that would behave, naturally form something like a cellular membrane. And they call it the azotosome, what comes out of this process. And this is just an early attempt of showing that organic chemistry could develop also without water. And this is very interesting, but has not been pursued very much at this time.
Well, thank you very much for sharing your insights, and thank you all for coming and your questions.
You get around. That's a nice.
Oh, I see. All right, let me, I have to get rid of this microphone, so let me.
Yeah.
It's not so irreversible for being a single object that changes the nature of the place and way. So at the moment, it's something people have only general
some things are like better untouched or wrong. Some things like they don't need inspiration because rather detriment the essence of it. Yes, so why is that you have also speaking such idea and interpretation? So in a certain way, something that we check and then we talk about and then we can start. Annars kommer han alltid så härifrån.
Thank you, sir.
Right now. The other finalists.
It was also
long term and explain to the customers as well to apply those scientific solutions, even though, I mean, they invest a lot of money even before they're building, so for them, they're already losing the money, so how to convince them to look a bit more long term as well. Thank you.
Would like to have a go with that?
I can start. I can totally relate to that. I was asked how much carbon or how much do you produce per square meter per day? And my immediate answer in the beginning was, okay, I need to set up an experiment and it depends on the sun, it depends on the nutrients, it depends on this and that. And okay, if you give me like 3 years and this amount of money and I need to replicate it 10 times and then I need to repeat the experiment. And then the industry says, what? We need a number. Okay, give us a number. No, I won't. And then give us a number. Okay, I give you a number. But then the factory is maybe 50% wrong. It doesn't matter. And I'm like, what? So we need to meet, talk to each other, get outside our comfort zones from both sides. And I mean, it was particularly hard for me as a scientist to step out. I don't know, your feelings about this?
And I guess
water matters to me because I think in this day and age, clean fresh water has been very scarce. So more than ever, I think looking for sustainable ways to maintain fresh water and help save our oceans has been very important.
I'm very much privileged to be part of this seminar and workshop, and I've learned a lot today. But yes, water matters to me because I come from a country where we have issues with water. First of all, it affects the mortality rate of the children, it affects the mortality rate of the mothers, and it affects the mortality rate of the entire nation. And there is need for water in Kenya. And we do have water, but we do not have the right technology in place to be able to put in the right infrastructure for the citizens. Also, you get a lot of children in areas like northern Kenya, which is in Turkana, where children are on the road asking you for water and not asking you for food or money. So we need to have an opportunity from the developing economies and see how we can be able to alleviate this situation. At the moment, I think it is a situation that's impacting in the entire emerging economy countries. And it would be really good to put it as a priority because water is life. We all need water. And it comes to us free, but we do not have the technology to put top-of-the-line infrastructure to be able to benefit from this precious element. So I urge the entire world to try and see how best we can resolve this problem with very little resources and make sure that it's sustainable. And today I attended the Solvaten water presentation, which I think would be very, very good for the emerging economies where the economy performance is not good enough for the local citizens to be able to have returns on investment, to be able to invest well on what they most need. So equipment like Solvaten becomes priority to Africa.
I'm from Indonesia, and thankfully when I grew up in my home country, we had enough water. Sometimes there are times where we had water supply cut-offs, and during those times it made us realize that we need to conserve whatever water we have left, and we need to use water wisely. Personally, I think that water is important for our health, and since most of our organs require water to function properly, we need water for hygiene and many other uses as well. So, yeah.
I'm from Italy, and water matters to me because since my childhood I've been a swimmer. So I used to be on a synchronized swimming team, and so just swimming in my spare time, if it's outside or inside. Now in my biomedicine studies, I realized how much water is important in a global health perspective. This summer I volunteered in India and rural areas where water is really a scarce resource, and we really need to take into account that it's a right to everyone to have water. So that's why it matters to me.
I think it's a smart
Same principle applies here, but in this case, permission will be given by our next guest, Marina Abramovich.
Okay, you had lunch, and now is my time, my turn. Water. We so much heard about water this morning, but we want to go farther than just talking about, but also experiencing in a kind of big group way. Many years ago, there's a Japanese scientist who took 2 glasses of water and experimented with them. 1 glass of water, they drink with extreme anger and frustration. And second glass of water, they drink tranquility with love and compassion. Then leftover drops of the water they analyze on the telescope. And they find out that the first glass of water, the molecules was completely disturbed and kind of uneven. And the second glass of water was complete in harmony and symmetrical. So one glass of water was poison, another one was healing and therapeutic. So it's really interesting how our mind can produce so many different things. It can, whatever you put in your mind and you put it out, you actually get it back. So it's really important how we can change consciousness. So now I would like you to actually bring this together, glass of water, the way I'm going to tell you. First of all, close your eyes. Second, don't cross your legs because you really kind of block the blood pressure. Sit comfortably. And just breathe, relax for a few seconds to harmonize yourself with energy with the water. And now we're going to just breathe a few times, really deep and slow, and gently hold with both hands glass of water without touching it. So, breathe in, breathe out. Slow as much air will go in, have to go out. 2, breathe in, breathe out. 3, breathe in, breathe out. 4, breathe in and breathe out. 5, breathe in and breathe out. 6, breathe in and breathe out. 7, breathe in and breathe out. 8, breathe in and breathe out. 9, breathe in and breathe out. 10, breathe in, breathe out. 11, breathe in, breathe out. And 12, breathe in and breathe out. Still with closed eyes, gently lift your glass towards your lips, but don't take a sip yet. Just feel the coldness of the glass and the touch with your lips. Just the coldness of the glass. And then slowly, slowly, let the water touch your tongue. And take first a sip of water. Feel the coldness. Feel how nourishing it is. How lubricating your entire system. And with the calm in your mind, the water pump, pure medicine. Start drinking slowly, as slowly as you can. We drink all this water so fast, without thinking, just in between things, between our phone calls or going from one place to another, or sitting at the table and having talks with the friends. But this is the moment here, tonight, to drink this water consciously, calmly, with the best energy you have to put in to this glass of water. Slowly, you feel the coldness, the wetness. Just visualize how it goes to every organ of your body and lubricate and nourish again and again. Slowly finish the glass because we have a limit of time. Otherwise, this glass of water can go for 1 hour minimum. And good news is you can keep your glass and do it the same at home. You know, I have this great joke about performance art. You say, how many performance artists you need to fix the light bulb? And the answer is, I don't know, I was there only 6 hours. So this glass of water should go a long way. Alright, so what I've been doing, I've been working with public art in collaboration to create some kind of video game, some kind of artist answer from my own point of view on these problems with the temperature rising on our planet and the water. So I want to show you just a short video first.
I think I was born as an artist. I remember nothing else than waking up in the morning and having ideas. To use this new technology in a different way is really important. How I can take video game, but how I can transform and translate it into something else that actually you can give another message to this whole concept. For an artist, it's the most important to find their medium, how to present it work. I was so lucky that in my career I found performance. When I put my body in the front of the public, something happened which is just different than when I was in studio and painting. It was some kind of electricity which arrived from the public and me, and every single molecule of my body became life. And I could take energy of the public and transform it and give it back to them. And I can push my body limits as far as I can go. I can do things that I never could do in real life. For me, it was very more important to explore the idea of the pain and danger, and to also be there in this present moment. Because performance art is timeless art. It's immaterial form of art. You can't touch it, you can't pin it on the wall. You just can feel it, and the public have to feel that energy. And then I've been introduced to virtual reality. And I understood that the possibilities of virtual reality are enormous. That whatever you can do, and you can't do with your body, you as avatar can actually do endlessly, and can replace you, and you can pass the body limits. And the avatars and VR technology are giving us this possibility to enter into this virtual space without our body. You can be present in so many places at the same time. It is very important that you understand immortality. You know, you're never there forever. Body's aging, and you're losing your energy, and you can't have all these strengths anymore as you had like you was 20, 30, or 40. So I had to face these kind of limits. So for me, to create an avatar and creating something that actually can stay without me being there.
So basically, this is a video game that I have to explain because we are not able to have 1,300 VR glasses here because it's just not possible. Yes, the technology doesn't have so many at the same time. But basically, when you touch my hand in the virtual space, you transport yourself into the middle of the melting snow. and you all personally witnessing the melting with VR glasses. So, what happened here is very simple. It's a video game in which you transport yourself into the melting snow in Antarctica and the South and North Pole. And if you don't do something which is good for this planet, I'm going to die in this water tank because I don't have water anymore and water is rising constantly. The piece is called Rising and have an actual metaphorical meaning. Rising means rising the water itself, which is evident, but also rising consciousness and how we can change something. You know, it's very interesting, the relation between scientists and artists. We have two things in common. We have intuition in common, and we have in common gut feeling, that you know you're right when you're going for something or you wanted to prove something. But at the same time, you know that unfortunately scientists have to have proofs, and we don't. But you have to have proofs, you have to work so hard to prove things, even sometimes proofs are, you know, so clear that actually you know these things as they are, but we don't believe them. I mean, there is a great example of some Dogon tribes in South Africa, which for hundreds of years been worshipping Pluto, the little trans-Pluto satellite around the Pluto, but nobody knew at that time there was any Pluto, the satellite, till the big telescopes was found and they said, oops, there's a Pluto. So then everybody believed. But this is really important that right now that kind of working together is very, very important. So what I'm proposing is very simple. It's a very simple pledge that we can all do in our own way, because nobody can change if you don't change yourself. It's so easy to criticize how the politics don't work, how the system doesn't work, how this is wrong or that wrong, but what we are going to do in our own simple way, in our own daily life. I mean, this is not, I just proposed 7 actually things to do. Very simple, very practical. Reduce the waste they create. Conserve energy and water, just by ourselves. Because, you know, it's so easy to look outside of us and don't see ourselves, that we are doing the same damage like everybody else. Use what I can. Be kind and respectful to all life forms. That's so important, because we always think that we are such a superior as a human race and not see the connection between everything, between us and nature and the plants and this planet we actually trash so terribly. Just a little story about trashing the planet. I was some years ago, I went to the Ponape. It's a tiny little island in Maldives. And there I went to, you know, just to walk on the beach. And the tourists took all the shells away. And the only shells, which there was no shells left, I saw the hermit crabs. It was hiding in the Nivea and the Ambre Solaire and the tops of the protection creams which was left on the beach. and they become their own kind of the home. And I was walking around with different colored tops around, and I got so sad by this situation that I took the boat and went 2 hours to another island, and on the market I bought 2 bags of the shells, and I brought back to the pond, and I put everywhere the shells for the hermit crabs to go. Wait, the story is not so, the story is not a good end. So I spent 10 days trying to get these hermit crabs into their shells. They like plastic better, so it's irreversible. We can't change that. Educate young people to go green. And the last one, I think the most important one, is contemplate 3 minutes for the well-being of the earth. And this is something that we have to really think about. If we just think about the earth, and the tiny little blue planet, we're not even in the center of Milky Way. We are in a kind of outskirts, we're like a New Jersey of Milky Way. Who knows where? And we are so tiny, so little, and we are living in paradise, and we trash it so badly. So to contemplate 3 minutes for the well-being earth, you can combine at home with drinking the water with the glass they give to you. So it's all really important. But the last thing I want to say is how it's important that artists, indigent cultures, who have the story to tell, who have rituals, who are so related to some kind of universal knowledge, and scientists should actually get together and make this big, strong community. It's not just enough one person. It's not just enough. There's something to change. You have to be on the large community scale. It's the only way, because I don't think that we can change things. I don't think that the planet we can save. Honestly, I'm not so full of hope. I only think what we can do is to slow the process, because it's going very fast. And so now, what I'd like to say is, the only way, this is my message, to change the world is to change yourself. Thank you.
We asked some of you what water meant to you, and put together a short video with some of your answers.
First, when I saw the small video about the water, I started to think, what is water for me? And first I was thinking about a first drink of water after the sport, and it's really like a present to make opportunity to have a fresh water.
In the current state of the world, when media and news tends to lean negative, and that's, as we were discussing, can garner more clicks and more people are interested in it. I think it's particularly interesting that the experts in the field are coming to us today with hope and inspiration for the future, and thus inspiring us to see that hope and to see what good might come.
I started to reflect on what comes first. Of course, if you have emergent and acute questions like health issues or access issues, I think the science literacy and the scientific aspect of it will become secondary to those immediate issues at hand. But I think if you look at it at the same time and in a holistic way, I think we can solve issues in a different way or approach them in a different way.
As a scientist myself, I would have also wished a little bit more deeper knowledge what we can actually do based on what we actually already know. So I'm always keen on going deeper into the matter.
And for me, I think maybe one of the points that resonated most is I always assumed that water waste had to do with leaving the faucet on at home or taking a shower that's too long. But to learn that actually the vast majority comes from the clothing that we pick or the food that we buy, it really kind of shifts your perspective. And that seems to be what the goal of an event like this is. So that's super interesting too.
Thank you all. I guess Marina Abramovich just told us what we can do. She beautifully made the connection between water and our bodies. And we're going to continue that connection now with a panel, this time involving Peter Agre and Randy Sheckman, and moderated by Jolene Zirath. So may I welcome them all on stage. Thank you.
All right, so as Adam has introduced, we're here to discuss the importance of water. And over the course of the day, I think we've heard a bit about how water is important for our planet and how water is important in our solar system and chemically. And I think you all experienced firsthand the physiological sensation of drinking a glass of water. But why is water important for our bodies? And so we have two experts, two Nobel laureates, who spent a good deal of their life studying the cell physiology of vesicle traffic and aquaporins. And so I wanted to ask the two of you to join me in a dialogue about the importance of water in our body. So Randy, why do our cells need water?
Water has unique chemical and physical properties that make it such an invaluable solvent for all of the macromolecules that constitute our cell. Its unique architecture and electronic configuration, with oxygen sharing electrons with the hydrogen atom, where the electrons tend to locate closer to the oxygen atom, impart a slight electronegative charge quality to the oxygen and a positive charge to the hydrogen, which allows a water molecule to form critical so-called hydrogen bonds within the structure of water itself, but in respect to our cells, surrounding biological molecules, where hydrogen bonds are critical for the stability of protein molecules in the cell and for the nucleic acids in our chromosomes, which form hydrogen bonds as the basis for the creation of the hereditary material. So water has a unique role, not only in the stabilization and formation of these molecules, it is a critical catalyst that participates in enzyme reactions, and it allows organelles within the cell to maintain a slightly different balance of the constituents of water. For instance, water, which you know is has a characteristic high concentration, is 55 molar, for those of you familiar with the term, but it's ionized at a very low level in just pure water with a concentration of hydrogen at 10 to the minus 7th molar and hydroxyl groups at a concentration of also 10 to the minus 7th. And a change in the balance of those two is what creates pH differences. The cell exploits those pH differences to create different compartments within the cell. The cytoplasm, which is approximately pH 7.4, but an organelle within the cell that is specialized for the destruction of macromolecules called the lysosome has a very special low pH, a high concentration of hydrogen atoms or protons that creates an environment that is conducive for hydrolytic enzyme activities. So all of these things are critically influenced by the water in our cells.
Sometimes I think it's a miracle that we just don't explode. So how do our bodies cope with water balance?
Well, Randy really eloquently described the importance of water within the cell. I'd like to just review potty training 101. Our kidneys are designed to clear wastes, maintain a proper blood pH, and water concentration. And this physiological process of releasing dilute urine under some circumstances or concentrated urine under others is one of the first physiological processes that mankind ever recognized. The Plains Indians in North America would wage war raids in the middle of the night with no method of measuring time. The warriors would simply drink a large volume of water at sundown, awaken 2 or 3 hours later to empty their bladders and go to town. every Friday afternoon at Johns Hopkins, the graduate students have a little party referred to as TGIF, thank God it's Friday. And you know the favorite beverage consumed is beer.
Not water?
So just imagine this, the graduate student drinks a half a liter of beer, or maybe a liter of beer. Where's the first place he goes afterwards? Not the laboratory, it's the lavatory. Alcohol has inhibited the release of vasopressin, the neurohormone, which sends a signal to our kidneys to concentrate water in some surfaces, but the alcohol will cause release large volume of dilute urine. Same individual the next day, playing tennis in the hot sun, underhydrated, now the vasopressin is released and causes the kidneys to concentrate. So we go between these two states. And anybody who's been on an economy class airliner with a full bladder, and the seatbelt light goes on, this is important.
So, you know, I've always learned as an environmental physiologist that by the time we recognize that we're dehydrated, we're already really dehydrated. Is that true? Is there a bit of a mismatch? Are we underhydrated for performing work?
It's certainly possible. And as we get older, our ability to sense thirst is less precise. Our abilities to sweat are reduced. Our abilities to concentrate urine also somewhat impaired. These are all aquaporin processes. So there are some consequences. When we're exposed to environmental stress, it can be life or death.
The water channel, which Peter's lab discovered, is critical for maintaining flow of water across membranes. Membranes are, to a low extent, permeable to water, surprisingly, even though membranes that surround cells are hydrophobic. Water's special properties allow it to permeate to a low extent through membranes. But the channels, the aquaporin channels, are critical. And as you alluded to, vasopressin influences the itinerary of that water channel in the cell. Cells maintain channels on the outer membrane of the cell, but they also have an internal reservoir of membranes that channels like the aquaporin channel can be held in, and that balance of traffic of the channel from the perimeter of the cell into the reservoir and back is critical for water flow across the cell. There are hormones, like you said, that control, promote a covalent change in the water channel, the attachment of a phosphate group on the water channel that influence its itinerary, and that affects certain disease processes. For instance, in cholera, the cholera toxin influences the state of phosphorylation, the attachment of phosphate to the water channel, and in patients who succumb to cholera intoxication, one of the first and most dramatic pathological consequences is the dramatic loss of water, because the water channel is retained and water flows out of the body at an alarming and uncontrolled rate. So water flow and its control is intimately tied to the membranes within cells.
Right, Randy. And our small intestine can release liters of urine, yet our large intestine is limited in how much water we can reabsorb. So people with cholera, and this is a problem in many underdeveloped parts of the world. In Yemen right now, where there's famine, there's also a huge cholera epidemic. This will kill thousands of people. And the ability to overcome that, we're limited. You can orally rehydrate people to a certain degree, but if the amount of fluid loss is beyond that, they'll succumb. Even in this late date in medical history, this ancient killer is still out there.
And yet there's simple remedies to that would be available.
Clean water.
Yeah, clean water. I mean, just the simple salt solution will also retard the rate of water loss in such patients.
Yes, the villagers in Bangladesh recognized that early on. A little bit of salt in the water will increase the rate of reabsorption and can orally rehydrate people and save their lives.
actually important as well for your work with malaria in terms of the aquaporins, so that you're using your basic science to kind of treat disease, and you gave the examples here. Could you elaborate a little bit on that?
Well, I grew up in an interesting family. My dad was a chemistry professor, very big on science and technology. My mother was a farm girl who went to university and always emphasized the importance of using our talents for the well-being of others. So I think medicine was a logical career because it merges both of those things. And as much joy as our laboratory got from a basic discovery, the urge was to immediately look for places where I can explain disease or maybe even prevent or treat disease. So our entry into the water channel field was a sheer accident. We were studying the rhesus blood group antigen red cells, and our preparations were contaminated with another molecule, which we had not a clue to its function. It turns out that's aquaporin 1. So the answer to how we discovered the aquaporins, I'd like to think that maybe they discovered us.
Sometimes it works that way. Hydration state of cells. How important is that just for vesicle trafficking? I mean, your whole life has been really studying how cargoes moved around cells.
But as I started to say earlier, the compartments within cells are generally barriers created by membranes that consist of lipids that are an insulating layer that by themselves preclude the passing back and forth of charged ions like sodium or chloride. So membranes, in order to allow communication between the cytoplasm and the outside of the cell or within a compartment of the cell, include channels, not only the water channel, but other channels that allow molecules, small ions to penetrate. In the last 15 years or so, new compartments have emerged which have quite interesting properties that are not bounded by membranes, but represent distinct soluble phases in the cytoplasm of cells that consist of protein molecules that are very often not folded in a tight three-dimensional structure. Instead, they have what are referred to as low complexity domains, sequences that allow the protein to be much more flexible. These protein molecules exist in the cytoplasm and can form a separate phase where the proteins interact with one another to some extent to the exclusion of water, and they often include RNA molecules, so they're granules, they're cytoplasmic granules that have RNA and protein. It's interesting to consider how that may have actually been the precursor of the cell. These granules don't require a membrane, and yet they are separate, and they can form and break in contact with the cell, and they may have even they may have existed before the evolutionary origin of the cell.
Do you see this in all different species? I mean, you see this in yeast, do you see this in bacteria?
It's in all living organisms, from bacteria to archaea to eukaryotes. These granules or separate phases exist in the cytoplasm, they exist in the nucleus. They are a relatively new organizing principle that is, I think, one of the more exciting developments in biology in recent years.
So if we go from cells back to humans, and we are all cells, a collection of cells, but if we take it to the whole body perspective, the emphasis on water, is that underappreciated in society or overappreciated? We've had a great day talking about the importance of water in our lives, but from a human health perspective, do you have any thoughts about that?
Well, when we have free access to pure drinking water, we take it for granted. And in human evolution, that was not always the case. So our kidneys have evolved so that we can maximally meet the proper body water content. The molecules that Randy was describing don't just float freely in water. They're packed in pretty tightly. The typical diagram of a cell, an open body with a nucleus, and maybe the folded in ER, the mitochondria, underrepresents the need to pack water pretty tightly. red cells, for example, filled with hemoglobin. That's the major component of the red cells. And if you look at red cells from all different species, compare a Gila monster or an alligator to a human, their red cells are different shapes, different sizes, vastly different, but the hemoglobin concentration is precisely the same. It's obvious that the water content determines that. And humans may bear the mutations for sickle cell anemia. Turns out the propensity of the sickle hemoglobin to polymerize is equated to the logarithmic concentration of water to the 32nd power. 1% increase in concentration will lead to an enormous propensity for sickle cells to have the sickling phenomenon. So I think these proteins are dependent on proper water in most instances.
It's a pretty fine-tuned machine we have.
Yes.
Could even affect the ability of molecules to form collections outside of the cell, such as amyloid in Alzheimer's disease. The formation of amyloid requires hydrogen bonds between proteins that are going to aggregate, and that obviously is influenced by water. Earlier in a panel discussion on where life may originate elsewhere in the universe, it was clear as I prepared for that session how important water was in the first evolution of life on this earth. Water appeared on the earth maybe as much as 4 billion years ago, but yet the evidence for the emergence of non-oxygen dependent photosynthetic organisms suggests that they may have followed very quickly within 200 million years of the first appearance of water on the earth. So that's how critical water has been for us, and I suspect it will be equally critical if we eventually discover life outside in other solar systems and elsewhere in the universe.
So if there's life outside, do the cells have water channels of the same structure that we have? I'd like to know that.
That's sort of leading to what I wanted to ask you guys about what's on the horizon, and I think that answers one of those questions. What do you think's on the horizon for us?
Well, in terms of water, or understanding the organization of the cytoplasm.
That's where your niche is, yeah.
Well, it's not just the water channel. There are other channels whose distribution within the cell influences cell physiology. One of the classic examples, similar to aquaporin, is a channel for glucose that's found in cells that respond to the hormone insulin. So there's a channel, a glucose channel molecule. It's held in a reservoir in the cytoplasm of the cell. And when cells first respond to insulin, and there's a breakdown of the storage form of sugar-bound glucose molecules, the reservoir of glucose channels held in a membrane is mobilized to the cell surface. They merge and display many more such channels to allow glucose molecules to be taken up.
The channels will be important for all of our biology.
Yeah.
So it hasn't escaped my notice that the two of you hail from the great state of Minnesota, and you've been brought up next to the Mississippi. And I think even you have a hero in, is it Huck Finn? Is that correct?
Well, yes, sort of a challenge.
So with that, I think you're, had an influence of water throughout your whole lives and careers. And thank you for sharing your thoughts and insights about the importance of water for our bodies. Thank you, Jim.
Magandang umaga, magandang tanghali, magandang gabi po sa inyong lahat. Ito po ulit si Carlos Polito, nag-uulat po para sa inyo dito po sa The Kaibigan Network. Andito po kami ngayon sa City of Stockholm, dito po sa bansang Sweden, para po sa Nobel Dialogue para sa Water. At bilang isang malaking karangalan po para po sa bansang Pilipinas, kami lang po tayo lang, ang Pilipino, andito ngayon para i-cover itong event na ito na napaka-importante po lahat sa atin. At gusto po natin paliwanag po sa lahat ng tao, ito po ay tungkol po sa tubig, na ang mga guest po, ang mga nagsalita po dito ay ang mga tao na Nobel laureate po. Ito po yung pinakamagagaling na mga tao na nabubuhay po ngayon sa balat ng lupa. At sila po ay nagbibigay po ng mga kanilang puro-puro tungkol po kung paano masasagip ang kalikasan, lalo na po ang tubig. At marami po kami natutunan ngayon, mga mamaya ho, yung mga andito po sa, abangan niyo po sa ating palabas po mamaya, ang mga iba-ibang mga speakers at mga taong ang sinasabi ay importante. At gusto po namin kayong anyayahan ulit na manood dito po sa The Kaibigan Network, ang inyong kaisa-isang Pilipinong online TV station na naglilingkod para po sa inyong lahat. Ito po ulit po si Carlos Polito, nag-uulat para sa The Kaibigan Network. Maraming salamat po.